Vous savez, aujourd'hui, nous parlerons des technologies Power-to-X avec Siemens Energy. Le Québec est en pleine effervescence avec la transition énergétique, l'hydrogène, gaz naturel renouvelable, etc. Puis le Power-to-X, il trouve vraiment sa place. Mais avant de parler de tout ça, permettez-moi d'inviter notre déléguée générale de Québec à Munich, Mme Elisa Valentin, à prononcer un mot de bienvenue. Mme Valentin.
Merci beaucoup. Alors, bonjour. Donc, je suis la déléguée générale du Québec depuis juin dernier et je viens par ailleurs d'arriver aujourd'hui même à Munich. Mais je voulais absolument honorer votre invitation pour laquelle je vous remercie. C'est un vrai plaisir pour moi d'être virtuellement avec vous aujourd'hui au nom du gouvernement du Québec, car le sujet de la transition énergétique et le Power-to-X est important, évidemment. La transition énergétique implique un effort important de recherche, d'expérimentation, de développement et de collaboration partout dans le monde. En ce sens, permettez-moi de souligner que les acteurs du Québec et de l'Allemagne, de par notre complémentarité et la force de nos écosystèmes respectifs, pouvons collaborer étroitement. The discussion today is a very important one. For example, with respect to green hydrogen that can be produced so efficiently in Quebec. Given the challenges of climate change, Quebec is fostering new technologies and markets in that field. Success will only be possible if we all work closely together to bring viable solutions to the market. J'ai hâte d'écouter les discussions qui rassemblent l'expertise de Power-to-X du Québec et de Siemens Energy. Since the creation of Siemens Canada in Montreal in 1912, Siemens has developed an important presence in Quebec in the fields of health technologies, industrial solutions, and energy. I am delighted with the active involvement of Siemens in this workshop today. Cet atelier illustre parfaitement comment la coopération au Québec entre les universités, les centres de recherche et les entreprises profite à toutes les parties concernées. J'aimerais d'ailleurs souligner la présence de Mathieu Payeur de Transition énergétique Québec, et aussi souligner que TEC a un partenariat avec DENA, son agence homologue en Allemagne. Energy transition implies a major effort in research, experimentation, development, and collaboration all over the world. The Quebec Strategic Cluster on Smart Energy, directed by Professor Louis Boulon, plays a key role in structuring a network of research and industry experts. Avec ce réseau, le RQEI accroît ainsi la création et le transfert de connaissances et forme de professionnels hautement qualifiés pour mieux relever les défis énergétiques. The Hydrogen Research Institute of the University of Quebec in Trois-Rivières, directed by Professor Pierre Bénard, who is also with us today, is well placed both geographically and scientifically to introduce Power-to-X technologies across Quebec's industrial landscape. At the roundtable today, we are going to hear from Quebec key stakeholders, such as Professor Umaru Savadogo of Polytechnique Montréal, Monsieur Pierre Ducharme from Olin, Monsieur Martin Simoneau from Hydro-Québec, and Madame Catherine Soriol from Energia. Je suis certaine que les discussions de cet après-midi seront enrichissantes. L'équipe de la délégation générale du Québec à Munich sera heureuse de soutenir la suite des échanges et d'encourager les collaborations entre le Québec et l'Allemagne. Merci tout particulièrement à vous, professeur Barnabé, ainsi qu'à votre équipe d'avoir organisé cet événement. Je tiens également à remercier tous les présentateurs et participants. Vous contribuez tous de manière significative aux avancées. Donc, je vous souhaite bon séminaire. Merci beaucoup.
Merci beaucoup, Mme Valentin, pour ces bons mots. Maintenant, j'inviterai Mathieu Payeur, directeur de Transition énergétique Québec, à s'adresser à nos invités et à l'auditoire. Mathieu.
Bonjour à tous. Donc, il me fait grand plaisir d'être aujourd'hui avec vous pour entendre parler du Power-to-X. Comme vous savez, je suis très intéressé à entendre les opinions et les opportunités que représente ce volet lié à l'hydrogène pour les bénéfices de la transition au Québec, transition énergétique évidemment. Comme plusieurs d'entre vous le savez, TEC a d'ailleurs rendu disponible une étude sur notre site web sur le potentiel technico-économique de l'hydrogène et on y constate en fait que la filière de l'hydrogène représente en fait un atout, un appui supplémentaire à la transition énergétique du Québec, notamment dans le vecteur de la chimie verte et de la mobilité, le tout étant en complément évidemment avec les autres technologies d'électrification. C'est vrai au Québec, mais c'est aussi vrai ailleurs dans le monde et c'est dans ce contexte que nous avons signé une entente de collaboration avec l'Agence de l'énergie allemande, donc l'INA, et aussi avec la France pour discuter et échanger sur différentes thématiques, dont l'efficacité énergétique et l'hydrogène. Avant de céder la parole au présentateur, j'aimerais aussi remercier le RQEI d'avoir organisé le webinaire et de contribuer par ses activités à favoriser la collaboration et l'échange, et surtout à canaliser les expertises autour des sujets prioritaires en matière de recherche en lien avec la transition énergétique. Je m'en voudrais aussi d'oublier de remercier l'ensemble des panélistes et des présentateurs qui vont contribuer à l'événement, et je vous souhaite à tous un très bon webinaire. Merci beaucoup.
Merci beaucoup, Mathieu. Now I will switch to English. We have with us today Chris Norris, Nakul Prasad, and Omer Rubio from Siemens Energy. They will make us a presentation, and after we'll have a period of questions with our panelists. So guys, you can now begin your presentation.
Okay, thanks very much. Thanks for the introduction, and thanks for the warm welcome to this opportunity to speak to you about what Siemens is doing in the green hydrogen space globally and in North America. Omar and Nakul and I have prepared a few slides, so if you just bear with me for a moment, I will share them. And here we are. Okay, so we won't take long. I think about 20 or 25 minutes is what we budgeted. I would like to provide an introduction to hydrogen and why it's so important to focus on green hydrogen now. Omar is going to talk a little bit about the Siemens portfolio offering of electrolyzers. And Nakul will talk about one use case, re-electrification and gas turbines, as well as a few other topics. And then we'll just wrap it up and proceed to the panel for discussion. So, I mean, I think we all understand the urgency and the importance of progressing the decarbonization discussion. CO2 emissions, of course, through the Paris Accord, demand a global reduction in carbon dioxide to levels that are going to be difficult by any measure to achieve. Baseload projections is a significant warming, and to achieve even Canada's own Paris Agreement targets are going to require a significant amount of effort. This is why green hydrogen is so important. I mean, shares in the global CO2 emissions show that buildings, transportation, and industry contribute a significant amount of GHG emissions. And what we're really focused on in terms of sector coupling, a term I'll describe in a moment, is really how do we decarbonize not just the areas of the economy that are straightforward to decarbonize, electrification of mobility and things like that, but how do we really decarbonize deeply and the sectors that are not easy to decarbonize. So hydrogen solves a couple of problems. And the solutions that hydrogen provides certainly vary by jurisdiction. We know that Quebec is a unique jurisdiction in terms of the way it produces energy. But ultimately, one of the things that hydrogen can do is be a store of energy in terms of intraday shifting from peak supply and demand, and also seasonal shifting in terms of long-term storage in various methods that are available, from direct storage of hydrogen to creation of synthetic fuels. Now, on the right, I think is really the essence of what we call Power-to-X. With e-hydrogen in the center, and on the left, we indicate the sources of renewable power, wind, solar, and particularly hydro in the case of Quebec. We really see that, you know, there are a couple of areas where the economy can focus on decarbonization through direct electrification. The top one is through heat pumps, for example, in terms of the building sector. My apologies. And of course, down below through mobility. But what we also see is through e-hydrogen, there are a lot of other sort of difficult to decarbonize sectors. For one example, ammonia, from which fertilizer is derived, produces on the order of 800 megatons of carbon dioxide per year, which exceeds global, the European production of GHG emissions from its entire electricity sector. So these unseen and less than obvious, especially to people who are not in the industry, sectors of the economy that consume a tremendous amount of carbon dioxide, or at least emit a tremendous amount of carbon dioxide into the atmosphere, are areas that have a primary interest in the sense of decarbonizing through e-hydrogen or green hydrogen. I think we're all here because we realize that Quebec is well poised to be a key player in the green hydrogen space. You know, one of the things that Quebec is known for is its abundance of clean energy. We see on the left an indication of where the GHG emissions come from by sector. And the electricity sector is too difficult to see, essentially, in 2017 and onwards. So that tells us that the target for decarbonization in Quebec is in these other sectors of the economy. Much of the discussion around grid modernization and decarbonization comes from the discussion around decarbonizing the electric sector, but in Quebec, clearly that is well in hand. The middle image, of course, showing what is widely known about Quebec, which is the vast majority of electricity comes from renewable hydro generation with a tremendous installed capacity of almost 37 gigawatts. And of course, on the right, showing that the hydropower is produced quite a distance from consumption and load centers. That is a challenge that's of course been addressed by Hydro-Quebec, and it provides potentially opportunities, especially in the areas where hydropower is produced relatively close to deep water ports and tidewater for export of commodities that are derived from green hydrogen. So the hydrogen economy will support CO2 reduction. Of course, depending on legislation and the early support of the industry, as well as the emergence of scalable solutions. Here on the left, we talk about what are the types of hydrogen. I mean, there's a global demand for about 70 megatons of hydrogen, and as a negative side effect, there's emissions of about 830 megatons of carbon dioxide per year, just in the production of gray hydrogen. And here we talk about the different, what we're colloquially using as the colors of hydrogen, but of course there's development in the sense of how are we going to define hydrogen in the form of its carbon intensity and also its source. And so I think this terminology will serve out its usefulness as we develop carbon intensity targets for different types of hydrogen. But natural gas, as you can see, forms a significant portion of the global supply of hydrogen, with renewable power providing only a small portion of it currently. But of course, that means that there is an ample market and a growing piece of the pie for green hydrogen. Now, how do we get it to market? Well, there's several ways. One is, pure hydrogen or blended hydrogen, and I think we'll probably discuss that more when Energiepark and Catherine speak about their role in the hydrogen sector, both from a pure hydrogen and a blended hydrogen point of view. There's also being able to move it from place to place in the form of liquid hydrogen or absorbed hydrogen. And then, of course, the synfuel and chemical pathway, the creation of methanol and ammonia, both are topics of significant discussion in Quebec currently. Of course, there's the re-electrification pathway, one that is focused on elsewhere in North America. And I think, one of the reasons we want to highlight that in this discussion is because, despite the large demand for hydrogen in Quebec, Quebec is not only a great provider of low carbon power for the production of green hydrogen, but it has a lot else going for it in terms of post-secondary institutions, research and development areas, and a lot of things that can service markets outside of Quebec, as well as storage. I mean, hydrogen can be, storage can be defined in multiple different ways. There's the storage of electricity where it can be re-electrified at a later time. There's storage in the sense of, using hydrogen to offset future demand. And then there's the type of storage that is involved with production of a substance that will offset the demand for electricity. And hydrogen really has a role to play in each of those storage types. And then from a consumption point of view, I mean, all I want to convey here is that there is tremendous demand for hydrogen globally for multiple different uses. And the question is, how do we use this opportunity to substitute green hydrogen for the type of GHG intense gray hydrogen that has been the source of most of the hydrogen in the past. This is simply an example to talk about a renewable energy farm, a wind farm, for example, a 200 megawatt wind farm in a power-to-fuel plant providing hydrogen through electrolysis through Siemens electrolyzers that Omar will discuss. Talking about transferring it to a liquid fuel infrastructure and getting about 280 gigawatt hours of green fuel from 560. And then the multiple uses in aviation and in transportation and in home heating that can be derived from this. So I hope this sets the stage for the reason that green hydrogen is so important, especially in the Quebec economy, in the Canada economy, and also in the post-COVID recovery stage that we're in the economy. And with that, I want to turn it over to my colleague Omar, who's going to talk a little bit about the Siemens offerings.
Perfect. Thank you, Chris, and thank you everyone here for the opportunity. I will be brief in my presentation, but I will basically cover some important points so that hopefully will trigger some thoughts and ideas for discussion later on. So Siemens has been in the business of electrolyzers since 2011, where we basically developed the technology and we did it at a lab scale demonstration facility where we eventually transitioned into commercializing the product line with the Silyzer 200, which is an electrolyzer that draws roughly 1.5 megawatts of electricity to produce hydrogen. Our current portfolio consists of the Silyzer 300, which is what I will describe in more detail in a little bit. These Silyzer 300 draws roughly 17.5 megawatts of electricity to produce 330 kilograms of hydrogen per hour on this electrolyzer. What's important about this slide is that we at Siemens have developed the technology in such a way that we are modularizing our designs to eventually scale up the level of hydrogen, the amounts of hydrogen that we can produce. So we started at, the kilowatt level, and we hope within the next decade to move towards the, more than 100 megawatts of hydrogen production. So if you can move on to the next slide, please. So when we talk about these electrolyzer, Silyzer 300, I mentioned already the draw of electricity. It has an efficiency of 75% efficiency, and it's a modularized design. And the reason for that is so that we can scale it up in the future in modules to be able to scale up to higher quantities of hydrogen production per day. So I mentioned that it draws roughly 330, well, it draws 17.5 megawatts of electricity, and it produces 230 kilograms of hydrogen per hour. If you move on to the next slide, please, Chris. So one important topic that we need to discuss is efficiency. And when I showed the first slide, I mentioned how we want to scale up the hydrogen in terms of production. In terms of efficiency, we expect that this will continue to also develop. However, there's only so much we could do with the thermodynamics or with the mechanical aspect of efficiency in this case. But our PEM electrolyzer, it has an efficiency per module of more than 77% efficiency. Now, when you start considering all the transformer heat losses, the rectifier losses, and all the auxiliary system losses, you basically get to the 75% efficiency aspect. These PEM electrolyzer that we have, delivers the hydrogen at atmospheric pressure, which means depending on the end use of this hydrogen, you will probably need to compress it. So when you add the compression and the cooling systems to the balance of plant, when you're doing an electrolyzer system like this, then your efficiency will go down to 74%. And then eventually you will end up roughly at 72% at the end of the entire balance of plant. So what I wanted to convey with this is that we can only tweak so much in each one of these aspects, and eventually, hopefully, we'll be able to continue to improve the efficiency to higher levels as we develop more efficient systems in each one of these auxiliary systems. Would you mind moving to the next slide, Chris? One important aspect of the Siemens electrolyzer is because of the background that Siemens has in the energy industry and power generation, right? We made sure that the Siemens electrolyzer provides good dynamic response. So one of the key characteristics of this electrolyzer is that it could be turned on within 60 seconds, delivering hydrogen, full hydrogen production within those 60 seconds, and then you being able to, as the operator of the electrolyzer, being able to ramp it, let's say, up and down in a dynamic response range between of 10% per second. So when you look at this, you can consider this as a grid support service. And when we talk about grid support service, we can think of many different aspects. But let's say for now we can oversimplify it as an electrical load that can satisfy demand response. And when we say demand response, we basically, the rectifier load of this electrolyzer can be up and with the full load being consumed within 30 seconds of the turning on the device. And like I said, then we can also turn it up and down at 10% per second as necessary. So would you mind moving to the next slide, please? So the electrolyzer itself, I mentioned it earlier, it's not only the electrolyzer, but it comes with the entire balance of plant aspect that needs to be considered when we're looking at Power-to-X aspects. I don't think there's much to talk about this here, just wanted to show a pictorial aspect. But what I do want to talk, and maybe on the next slide, is that Siemens has a vast, would you mind moving to next, Chris? Thank you. What Siemens does have is it has a vast portfolio or array of equipment throughout the entire value chain of this aspect. The core of this is basically where you see the purple boxes, where we have a lot of transmission and distribution equipment that can be put in place in a Power-to-X project. The electrolysis, which is something I just mentioned, and then all the compressors and the mechanical devices that we have from our industrial applications solutions. So when you think of a Power-to-X, and let's just consider a power-to-liquid type of project, the synthesis aspect is something that Siemens does not necessarily have in its portfolio. However, this is something that we typically would partner with companies that have that expertise and the capability, so that we can provide our customers with a full solution array. Would you mind moving to the next slide, Chris? So with that, we just got to a few, I wanted to show you two business cases and examples of references of what we have done. So one of those is the Energiepark Mainz. It's a project in Germany, which it was installed in 2015. It's a Silyzer 200. And the interesting thing about this application is that it receives energy from a wind farm nearby, and then it produces green hydrogen, where this green hydrogen is used for a multiple of uses. One, it is blended into the natural gas grid, right? Then it's delivered as a feedstock to surrounding industrial companies like fertilization, for instance, or for the use of fertilization. And it's also used for local hydrogen fueling stations for the transportation sector. So this is a good, let's say, showcase for the entire application of Power-to-X technologies. Then if you move on to the next slide, please, we have these H2FUTURE project, which is a project in Austria where it is using an electrolyzer to produce hydrogen, and the hydrogen is being used on what is considered a breakthrough steel making technology process, where the carbon that is typically used in the steel production is replaced completely by the use of green hydrogen. And one of the use cases that this has is not only for steel making process, but also the electrolyzer provides some, let's say, dynamic response capabilities for grid support services in the Austrian region where it works. And with that, I would like to pass this on to Nakul.
Yeah, thank you, Omar, and yeah, good afternoon, everyone, and good evening, and thanks for joining. Pleasure to be here, and I hope you're all safe now. I think safety is the biggest asset and the biggest thing we need to take care of now. So what I would like to sort of continue what Omar was saying. He was showing a couple of examples of Power-to-X, and just to recall, X can stand for anything. It can be chemical, it can be heat, and one of the use cases of Power-to-X is power-to-power. And I want to highlight this recently deployed project, of which will be operational in 2023. It's called HYFLEXPOWER. It's funded by the European Union, where Siemens is participating with a number of other industry and university partners. And this unit is going to essentially take renewable energy from the grid, convert it through Siemens electrolyzers into hydrogen, and then co-fire it in an SGT-400 gas turbine. And the unit is going to produce 12 megawatts of electricity and additionally 20 megawatts of heat. So that's very crucial. It's a combined heat and power, so it's very efficient, high fuel utilization rates of above 90%. Another advantage of this unit is it can burn hydrogen, natural gas, and any blend in between. And that highlights the value of gas turbines in such a hydrogen economy, because it's also about energy security and affordability. And this unit additionally is already operational. It's going to be retrofitted, so it's going to receive minor upgrades like burners and so on to accommodate the hydrogen level. So it's really fulfilling all aspects of the energy trilemma. It's always dispatchable, so it provides energy security because it can switch between hydrogen and natural gas at any time. It's affordable, so it's an already running asset which has some upgrades, so it's really a capital expenditure which is not too high. And it's sustainable because it can burn up to 100% hydrogen, so we won't see any CO2 emissions with this engine. So that's a very nice project, a very nice showcase of another example of Power-to-X, specifically power-to-power. And Chris, if you go to the next slide, please. And that brings us to the gas turbine part. So as we've seen, gas turbines can play a very important role in this hydrogen economy because we have 10,000s of gas turbines running already worldwide. So upgrading these gas turbines is not a, let's say, it requires some effort, but it's a manageable effort in terms of capital expenditures and R&D. So to give you a bit of a snapshot, A, about our portfolio of gas turbines, and B, what they can already burn in terms of capabilities of hydrogen contents. The graph is shown here. So you can see in our portfolio, we have gas turbines ranging from 4 megawatts roughly to close to 600 megawatts in simple cycle. And if you run these engines in combined cycle, then obviously you're close to a gigawatt at the maximum power output. And the range from 100 to 600 megawatt is what we refer to as utility scale, and the smaller range is the industrial scale gas turbines. So on the utility side, we can see that most of the, or actually all the engines are already capable of burning 30% by volume hydrogen. And that is using low emission burners. So dry low emission burners meaning there's no water required to abate your NOx. So they comply with any NOx regulations like 15 to 25 ppm without using any additional water. We have a range, the A65, A45, and A35, which are aeroderivative units, and they can be delivered both using dry low emission systems as well as wet low emission systems. So wet low emission systems being diffusion burner, conventional burners, but using water to abate NOx. And these engines can already run up to 100% using these WLE burners. And then the medium-sized range, the STT 800, 600, 700, they're already capable of running dry up to 60%. And as we've seen in the previous example, the STT 400, for instance, will be able to run up to 100% by 2023. So we see there's already a strong capability across the portfolio, and that's also driven by the history. So hydrogen is not a new topic. And specifically for gas turbines, it's been a talking point because hydrogen often appears as a waste gas in industrial processes. So in refineries, for instance, or even the steelmaking process. And there's two options: either you flare that gas or you convert it into energy. And that's what gas turbines have been essentially doing for decades now already. And if you go to the next slide, please. So we've seen 30%, 60%, and so on. But to really reach our ambition of decarbonizing the entire fleet, so running on 100% hydrogen, and in fact, we've made a pledge to do that by 2030, still requires a bit of development. And that's shown by the graph here what the challenges are. So a couple of things about hydrogen. Obviously, it doesn't produce any CO2 because it doesn't have any carbon bound, but it has other challenging properties which need to be managed, especially when combusting these gases. So it's got a higher diffusivity, it's the lightest element, so it's very diffusive. So we need to make sure that all the sealings and piping systems are all managed to accommodate hydrogen, avoiding embrittlement, for instance. It has a lower volumetric energy content, so overall you need larger volume flows to be handled by the fuel system. But the key point is really hydrogen is very reactive. Everybody knows it. It's very explosive. So what it does really is shown in the graph here. On the x-axis, you can see the content of hydrogen per volume. And on the y-axis, you'll see different physical effects here. So the orange line is showing the so-called flame speed. That's kind of characteristic for the reactivity of the flame. And as you can see, at 10%, for instance, in these images, so just for orientation, the flame is sort of moving from down to up. So the flow is moving from down to up. We can see that the flame is very distributed, somewhat anchor downstream of the combustor. But as we increase the flame, the content of hydrogen, the flame moves faster and faster towards the burner. And 90%, we can see the flame is very compact, very much attached to the burner rim, and it's very faint as well. So there's some detection issues as well. And the orange line is kind of quantifying what we're seeing here in terms of the relative flame speed. And you can see that kind of exponential increase. So from, let's say, from 0 to 30%, we don't see that strong reactivity increase. But as we move towards 100%, we see that increase sort of exponentially increasing. And that also shows the challenges. So we've seen in the previous slide, a lot of engines can already do up to 30%, but reaching 100% still requires quite a bit of work. So that's something we need to overcome. And we do this shown on the right in a rapid prototyping cycle. So our CFD, our design tools have become much better, computational fluid dynamics. Now we can do time resolved simulations of the flow field. So that allows us to do more high fidelity optimization, even automated. And we can print these designs very quickly now using additive manufacturing. And additive manufacturing is a core component now at Siemens, a core manufacturing design, which has not only helped us improve the speed of these designs, but also giving engineers now just more leverage to play around with much more sophisticated designs, which they couldn't manufacture in the past. And then we need to test this in a high burn pressure testing rig. So first in a test rig and then in the engine, because it needs to be full pressure, because all of the effects shown before, such as the flame speed, these are effects which amplify at pressure. So it needs to be tested in engine conditions. And once we've done that cycle, optimized the burners, we then go into the full engine. And if we go to the next slide, just one recent example for one of our engines. So that's an SGT 600 engine, which is about 25 megawatt rated. And we started this, really did a bit of CFD, then we went into an atmospheric test rig. to try and see, okay, how is the design going? And we managed to get to 100% using dry low emissions. So that was a good achievement. As the next step, we went into a high pressure test, and we were able to reach up to 100% again. So that kind of validated what we've seen. However, we saw that it increased NOx, so at about 40 ppm as compared to 25 ppm what we're offering. But that was just the first run. That was a really good testing experience, because a lot of the challenging effects such as flashback and other thermoacoustic effects were not prohibitive in operating this burner. So as a next step, we actually went into a full engine. We did some engine tests. We were able to replicate quite a few tests what we've done in the high pressure test rig. But since this was sort of design version 0, this now went back into the design cycle. So hopefully we're going to see this develop very rapidly and then offer this engine commercially at 100% DLE in the next years. And if you go to the next slide. Yeah, finally, it's just to sort of add again, talking about stranded assets. So I mentioned there are 10,000s of units operating. And stranding these assets is not an economical choice, especially since gas turbines are very flexible and are actually very good peaking and renewable backup solutions. So upgrading these units to hydrogen is really a future-proofing as well of these units. And when we upgrade a gas turbine package, just schematically shown here, of course, that depends on a variety of conditions such as the engine model, the boundary conditions, the site conditions, the local requirements, and so on. But basically what we need to do is look at the fire protection systems, make sure the electrical equipment is upgraded to accommodate hydrogen, looking at the auxiliaries as well, and things such as mentioned, such as ceilings, piping systems, and so on. But the main one is really the burner adjustment and the exchange. But the majority of the core remains unchanged. So that's also something which is very sustainable. And whatever we do in terms of new unit development for gas turbines is something we aim to retrofit into most of the versions of the already operating assets. So again, it's bridging the future and the present through this kind of sustainable path via upgrades to gradually decarbonize existing assets. And if we go to the next slide, that is already, I'm already at the end of my talk. I'll hand it over back to Chris.
Thanks, Nicole. Yeah, I just needed to get off mute. Okay, so thank you very much, Omar and Nicole, for that presentation. I think just to sum up, we've talked about the importance of decarbonization in the energy system and the role that low carbon fuels, including hydrogen, play in that. We've talked about sector coupling, which is not just electrifying industry, but in electrifying those very difficult to electrify industries, chemicals, petrochemicals. We've talked about Power-to-X. We've talked about taking hydrogen and going to many different uses. Nicole gave us examples as they pertain to gas turbines. Certainly, it's power generation by gas turbines is more of a directly related subject in many of the other areas in Canada. Of course, with Quebec, with its high hydro penetration, it's less direct. But the reason we wanted to spend some time on that is because the hydrogen industry is going to have so many other follow-on effects in order to make it a reality. We know that Quebec has a strong aerospace industry, and Siemens is part of that with respect to our aeroderivative gas turbine engines. And ultimately, the move to hydrogen does require a change in regulations, not just codes and standards, but also incentives to enter into a marketplace that is well established, but with a product that has this great attribute of being low carbon. And with that, I want to say thanks again to Madame Valentin for the introduction. I think your role and your presence here emphasizes the importance of collaboration between Quebec and Germany, and between organizations within Quebec and Siemens itself. So thank you very much for taking the time to introduce us. And Mathieu Payeur from TEQ, the importance of collaboration. I mean, we emphasize that. We have a strong footprint, as was mentioned, in Quebec, and we want to strengthen that. Professor Barnabé, Simon, and Stephanie and Raphael, thank you very much for this opportunity and for coordinating everything and bringing us to this audience today. And with that, I look forward to the discussion with the panelists. Thanks very much.
Yes, great. Thank you guys for your presentation. You show us, you give us some technical information. You spoke about technical challenge, and you have present some showcase flagship project that we are dreaming in Quebec to have. You know, we have many Quebec organizations that are preparing the field for that. And speaking of Quebec organization, we have some today that will ask you question. If time remaining, we may ask to the audience some question, but I don't think so. So I am inviting the audience to write their question on the chat room, and maybe you can answer to them, or maybe after we will see what we will do. But now let me introduce the panelists, the Quebec Organisation representative. I will do it in French. Nous avons aujourd'hui Madame Catherine Soriol, qui est responsable du développement du gaz naturel renouvelable chez Énergie. Nous avons avec nous aussi Martin Simoneau, chercheur à l'IREC, responsable des dossiers sur l'hydrogène. Nous avons Pierre Ducharme, qui est directeur régional des opérations canadiennes chez Olin Canada, mais qui est aussi président de développement économique Bécancour Inc., qui pilote entre autres le projet de zone d'innovation de Bécancour. Et enfin, nous avons notre représentant universitaire et aussi un expert en hydrogène, qui est le professeur Oumarou Savadojo de l'École polytechnique de Montréal. So thanks for being with us today, everybody. And we will begin the period of questions with Mrs. Soriol.
Est-ce que je devrais les poser en anglais? J'imagine que oui.
Oui, s'il vous plaît.
Parfait. So thank you for the presentation. It was very insightful. I had, I'll go quick on my questions, but I had maybe one question on your slide 9 that was mentioning the PEM evolution. So having the technology going up by a factor of 10 every 4 to 5 years. We understand that the PEM is the core of the hydrogen pricing, and to make the green hydrogen eventually competitive to the gray hydrogen, we're focusing on scale. Are you foreseeing the price curve of green hydrogen to eventually go in the same direction as the evolution of your PEM sizing? And I know you addressed the efficiency, which would be hard to tweak or to better over the years, but could you just speak to the fact of how you're foreseeing the pricing of hydrogen in the future?
Yep. So I think the pricing of hydrogen will so the pricing of green hydrogen is primarily driven hugely by the price of electricity, right? So the price of electricity will drive how much slower green hydrogen can get. For it to be competitive, even with conventional methods of production of hydrogen, obviously you need to have access to cheap electricity price. So if we try to compare electrolyzers, right, whatever technology, to produce hydrogen with with methods of renewable energy like wind or solar, and the way wind and solar technologies very rapidly went down within a decade in terms of price, I think in the hydrogen aspect, we will see improvements, but not necessarily similar, because the drive is primarily by the electricity price and not too much by technology per se. Does that?
Can I just add to that? I just want to add to that. So that's the one aspect of the electricity cost. The next one is obviously the capital expenditure. So I think key really to reducing that is going to be scalability. So we need to go to much larger scales to be feasible. So that's why Omar was showing that kind of development timeline where we need to go to gigawatt scales. I mean, that is really key to driving the costs down. And the next element which goes into it is carbon taxing incentives. I think if you combine these through, and the fourth one, by the way, so we didn't mention, is the capacity factor of the electrolyzer as well. So if you just run it as a kind of a peaking unit 4 hours a day, then obviously it's not that economic. So if you're able to maximize utilization to 24 hours, then suddenly you can see that already today, and we've seen use cases in Chile, for instance, where you have high capacity factor wind that drives high capacity factor electrolysis. You're at competitive prices similar to that what you get for gray hydrogen already today. So it's possible already today, and with all the regulations coming in, capital costs coming down, and so on, definitely there's a path there that it's going to be economically viable. Sooner than projected, that's my personal speculation.
Okay, thank you.
Or you can ask another question if you want, Catherine. Let's go.
Sure. So I was interested in your pilot project that you were mentioning in Germany, where you are also injecting distribution grid. So just wondering if you have the percentage that you are injecting in that grid at this point.
I don't have the answer for the specific project, how much it is. My speculation or assumption is that it's not higher than 10%. There's been studies made, or there are actually studies being made into what is it that the gas pipelines can take. It's typically assumed that 20% is a safe, a safe blend in pipelines, but there is studies being made primarily in Europe to increase that percentage of volume of hydrogen that the pipelines can take.
We've seen those studies also through the Canadian Gas Association here in Canada, and I think, Catherine, with your role at Energier, you may have some insight into the levels of hydrogen that would be capable of being injected into distribution systems as well as transmission systems with specific regard to hydrogen embrittlement and the other engineering aspects of
Exactly.
Okay, great. Great. I suggest to go with another panelist after we can come back to you, Catherine. Martin Simoneau from Hydro-Québec. Do you have some question?
Yeah, maybe my question would be directed to Catherine, and the fact that there's an issue about how much hydrogen can we put in our network, in the network, and this convolutes the way that we're going to process to either create new pipelines or use the one that we have. So you just heard that in Europe they're looking at 20%. What's the status of the volume that they can put in the gas grid right now in Quebec?
So it's still something that we are that we're monitoring. We have to. There's literature about it, and there's different demonstration projects around the world which we're looking at. But we have to also make the demonstration within our network to be comfortable with the higher percentage of injections. So it is something that we are looking at, but we're not at a point currently where we can speak to exactly how much, if we're looking at, let's say, doing RNG from third generation, so methanation, or blending hydrogen, how much exactly the network could tolerate in Quebec at this point.
Okay, thank you.
Good. Another question, Martin?
Well, I already spoke to the Siemens guys, so I'm pretty much all my questions have been answered already. So maybe.
Okay, good. Pierre Ducharme, it's your turn now.
Yeah, hi guys. I haven't spoken with you up to this day. I'm a bit of an unusual player, wearing a lot of hats, and in my community, we took the initiative of developing a proposal that is specifically addressing the need for clean energy, and hydrogen generation is part of the business plan that we're going to discuss with our provincial government, not within a few months, within a few weeks. This coming autumn, we will go to a table where our authority are proposing some means to finance some research on innovation. I could have a pretty simple question, which is, what do you need? And we'll make sure that our community will make available some resources. And that's why I'm here today. But I have also a background where I'm a hydrogen producer. I have 40 years of experience in cell rooms and different stuff. I have customers that buy our hydrogen. I have a customer across the fence that produces H2O2. So there is products like what I would call energy sector, like what you've been introducing us today. We're probably a little different having hydroelectricity available to us, but that hydroelectricity offer opportunity for green hydrogen, yes, to be used to store energy when we don't need, when we have excess energy available, like where we are positioned right now. And my question for you is, how could we team up to kind of meet your need? And here, what we pretend, how we're going to be different is that you have a network of large industries that goes from aluminum smelter, chlor-alkali, different chemical producer that need energy. We even attempted getting a fertilizer plant built, but it was kind of pushed back because of environmental reasons. So the fertilizer market, as one of your slides is showing up, is something we have made an attempt but failed. And we have a market, but we import. Our population doesn't want us to produce our material because it would be too bad in terms of CO2 emissions. So long detour to say, how can we work together and what would be the need for Siemens other than maybe specifically energy generator that would be fed by hydrogen or blending hydrogen into a natural gas distribution network like we have here, obviously through energy.
Well, maybe I'll take the first crack at that and then invite my colleagues to chime in. I mean, what do we need? I think what we need to do is look at the components of a successful green hydrogen project. Of course, there's the production, but really one of the key questions is in this hydrogen economy, green hydrogen economy, we need to grow two things at the same time. We need to grow the supply side and we need to grow the demand side. So from a demand point of view, we need an off-taker for a tremendous amount of hydrogen, green hydrogen. You know the hydrogen market better than we would, having been a player for so long. Looking for off-takers who are interested in green hydrogen, which as a commodity is exactly the same as any other type of hydrogen, but of course has the preliminary upfront aspects of the low carbon part of it. So, you know, in a lot of the business development that I do in North America, the question is, who's going to buy this stuff? Like we have people coming forward with investment proposals, with sites, with history, with power. And then the question is, what are we going to do with all of this stuff? So even from an agriculture point of view, I mean, if agriculture, if ammonia was rejected on the basis of environmental reasons because of so much carbon dioxide production, then that means it's right in the sweet spot for green hydrogen production, because all the rest of the components of that process, the Haber-Bosch process to produce ammonia, are well, you know, battle tested, tried, tested, and true, and they just need a new source. So what do we need? Well, we need offtake agreements. And then we need low-cost power. And when I say we, I mean the overall project, because I think there's many roles. There's the role of the off-taker, the role of the consumer of the hydrogen in the sense of producing whatever commodity that you're going to use downstream. There's the role of Siemens, which on one of the slides that Omar showed, shows that the electrolyzer is one component of the solution, but there are other components of the solution that Siemens can do, everything from engineering and balance of plant to finance. We do all of those things, but we are not ourselves project developers. And so we need to look at all the components of a successful project from the finance, from the engineering point of view, and also from the risk point of view. I mean, we are entering a new world in the type of volume for green hydrogen that we're looking at. And so the question to us becomes, how do we allocate the risk across the partners in a way that makes sense? You know, who are the debt providers and what do they need for this project to be bankable? Who are the equity providers and what do they need to see from a return point of view? What's Siemens' role and how much can we allocate risk to this project? How much skin in the game can we have? Because that's more of a question that seems to be coming forward lately. We're no longer just a solution provider or an equipment provider. We are a project partner. And then it's going to depend also on on the off-takers and what risks they assume. And government has a huge role to play in this from a de-risking point of view. So I hope I covered your question too.
No, it's excellent, Christopher, and I think I will pursue that discussion offline, because I know that all of the answer that you are in need of, other than your technology, the government provided financing and support, and we have a market where we are importing, and we are obviously a location where energy, clean energy, is relatively cheap. So I think there is certainly a very, very good potential to go back and revisit the idea of just, I'm not in the fertilizing business, but obviously I'm the neighbor of these guys who attempted that, and I know them quite well. So this is just one example where our location could become a kind of a large pilot plant, not a small scale, but because we are an industrial park, one of the largest in Canada, where we could probably, if technology is fine-tuned to the degree that people are ready to take the risk, as you rightly mentioned, they could be pretty interesting development in pursuing a dream of making at work a green hydrogen.
That's good. That's good. Thanks, Pierre, for your question. Thanks, Chris, for your answer. Now we'll give the chance to our university representative to ask question. Professor Savadogo, can you ask your question? We are hearing you. You can.
Est-ce que vous m'entendez?
Yes.
My question is regarding that general question always asking related to the fact that using renewable energy to produce hydrogen, and after using this hydrogen to make electricity in a gas turbine. And if the people ask why not use directly this renewable energy by using some storage system and directly use it in connect to the grid, or using it directly in electricity. That's always the question, but I don't know what type of answer you can have in this case. Because you know also renewable energy have some problem of they are not continuous, and we need some storage, and why in this case having a study case for producing hydrogen for PM electrolyzer and use it after in a gas turbine. I don't know if you have some comment.
Yeah, I mean, I can address it, and I think the question is valid, of course. One can argue why not directly electrify in a fuel cell, for instance. And I think we have to look at it case by case. Again, Power-to-X means a variety. And I think the prime use for hydrogen in the future, Power-to-X, is going to be mobility, industry, and so on. But it will also leave some space for hydrogen and gas turbine. And it's because of the flexibility issue. And if you're, let's say, you're completely off-grid, you're somewhere remote, you need that flexibility solution, you want to be green, you want to have a backup solution, that could be an option to have this power-to-power system where you have renewables and then convert it into hydrogen and then sort of feed it back through a gas turbine because it's very reliable. That being said, I mean, again, it's not the prime case. But why we also showed the hydrogen case in gas turbines, we've also seen that green hydrogen is not the only source for hydrogen. So we can also produce hydrogen via steam methane reforming and use carbon capture. So that's also a net zero fuel. And when we think about this supply chain, so let's say in the US, for instance, where there's plenty of shale gas, there's already pipelines which need to be upgraded, and you convert them into these hydrogen systems, for instance. Then every gas turbine is more or less connected. And we're seeing a lot of these RFIs now coming out in the US that they're requesting a minimum 30% and so on for gas turbines. So that's sort of on the other side of production as such. But again, to your question, again, to summarize it at the bottom line there, it's really valid. If you have renewable energy production of hydrogen, there are definitely better use cases than re-electrifying it. But re-electrification can be one use case. Depending on the condition, it can be a very attractive one. And in this case, as we've seen, since it's a combined heat and power plant, and the conditions are favorable in that specific HYFLEXPOWER project, in that case, it's a very viable solution and a cost-efficient solution, because we have an existing gas turbine which we just need to upgrade, which from a capital expenditure point of view is much less than building a new fuel cell plant, for instance, especially at these scales. I hope that answers your question.
No, yes, you asked the question. So I have some other questions, but I think it's better I will send you some email and we can exchange in some other aspect.
Absolutely.
I did also your presentation before,
Yes,
so
that's good indeed, because we are already running out of time. Yes, we made a short webinar. That was the idea also, short and sweet, as you can tell. But yes, we have also some questions from the audience. But I propose that we'll answer to that question after the webinar. Siemens Energy, our guests will answer to them, and it will be available on the answer will be diffused on the website of the Réseau Québécois sur l'énergie intelligente. So do not hesitate to send us a lot of questions, and you will get the answer a little bit later. So that's it. So we'll end that on this. Today we have introduced Siemens Energy to our energy transition smart energy community. We hope that it will lead to new collaboration with Siemens Energy. Let us say that Siemens Energy and its new new energy business are very welcome in many places and many sites and many areas of Quebec. So, so thank you again, guys, Chris, Nakul, Omar, for being with us today. And we hope that we will continue to have an interesting webinar like this. So now we'll go to French. I will go back to French. So, merci à tous les invités d'aujourd'hui. Merci à tous les participants aussi, spécialement la délégation du Québec à Munich, Transition énergétique Québec et tous les partenaires du Réseau québécois sur l'énergie intelligente. La présentation va être disponible sur le site du Réseau québécois sur l'énergie intelligente, ainsi que les réponses aux questions. Ensuite, dites-vous qu'il va y avoir encore plein d'autres webinaires organisés par le Réseau québécois sur l'énergie intelligente. Le prochain va possiblement porter sur la gestion intelligente de l'énergie dans les serres. On pourrait peut-être inviter aussi des gens comme Siemens Energy. OK, good. And, c'est ça, donc pour en savoir plus, on vous invite à vous inscrire au bulletin d'information du Réseau québécois sur l'énergie intelligente ainsi que celui de Transition énergétique Québec. Alors, on termine là-dessus. Merci beaucoup à tous, puis on se revoit la prochaine fois. Merci.